workshop. And our opening speaker for this session is Adrian Raftery of the University of Washington. And I learned many things from Adrian Raftery in my 16 years at University of Washington. Many statistical things, many cultural things. And one of the cultural things that he imparted to me was the utility of knowing to whom you're speaking during a seminar or a lecture. So, in fact, Adrian started a seminar series at the University of Washington where he insisted that at the beginning of every seminar we go around the room and introduce ourselves briefly. So Adrian requested that we do the same here because we are a somewhat diverse group, and it might be good for us to get to know the people we haven't already met. So I'm Peter Hoff. I'm at Duke University now in the statistics department.
Yeah, if you could say, your first and last name and your institution and what your discipline is, because we're as diverse.
Get out of giving a talk. It's going to take us half an hour.
No, it's not.
It's coming out of his time.
It'll take 90 seconds.
Okay.
Also Carol from Oxford Stats.
Could you do a bit of volume, please?
Yeah, shout.
Also Carol from Oxford Stats.
I'm Mikkel Schmidt from the Technical University of Denmark, DG Compute.
Niall Friel from University College Dublin Statistics.
Matthew Penrose, University of Bath, Mathematics, Probability.
Simon Luna Gomez, UCL, and Statistics.
Brendan Murphy, University College Dublin Statistics.
Talia Buchkina, University of Edinburgh Statistics.
Lisa Couture, University of California, Santa Cruz, Computer Science.
Jane Hutton, University of Warwick, Stats and Philosophy.
Sheila Bird, formerly of Medical Research Council's Biostatistics Unit, Biostatistician.
Magdalena Strauss, PhD student at the Biostatistics Unit.
Mohammed Masri, PhD student in statistics at McGill.
Chris Nemeth, Lancaster University Statistics.
Matt Hunes, Lancaster University Statistics.
Ines Cecilio, I work at the Schlumberger Research Center here. I'm an engineer, not a statistician.
All the best statisticians are engineers.
Mike West, Statistics, Duke University.
Ryan Kay, Oxford Stats.
Peter Arbenz, I'm a computer scientist deployed in the stats department.
Yasiri Knott, I'm in statistics in Hebrew University of Jerusalem. I belong to another group here, so I'm like fun.
Gesine Reinhardt, Oxford Statistics.
Ron Devonshire, Brunel University Statistics.
Harry Crane, Rutgers Statistics.
James in University College Dublin Statistics.
Chris Holmes, Biostats, Oxford University Statistics and Department of Medicine.
Sergio Bacallado at Cambridge Statistics.
Berto Kaimo, Dublin Institute of Technology.
Lisa Kirichenko, University of Amsterdam Statistics.
Steve Barron in Statistics at the University of North Carolina.
Joshua Cape at Johns Hopkins University Department of Applied Math and Statistics.
Harry Krieb, Johns Hopkins University, a frequentist.
Harry Zoll, Yale Statistics.
And at the back, introduce your city name and affiliation.
Peter Bickle, University of California, Berkeley.
And statistics, right. Okay, well, thanks so much. It's really great to know who I'm talking to, so thanks for doing that. I'm Adrian Raftery, University of Washington. I'm a statistician and I'm a professor of statistics and sociology. So I want to talk about dynamic latent position models for bipartite social networks. And this work is very much motivated by an application to interlocking company boards, which I'll talk about. And the new model we developed was very much dictated by the needs of this application. And this is joint work with Niall Friel, who's here from University College Dublin, Riccardo Rastelli, also from UCD, and Jason Wise from Trinity College Dublin. And I would like to acknowledge support from Science Foundation Ireland and also the United States NIH. So some background to the motivating application. This is a plot of Ireland's GDP per capita from 1999 to 2013, and in purchasing power parity, and it sort of encodes quite a dramatic story. In 1999, the Ireland's GDP per capita was $20,000 per capita, and by 8 years later, by 2007, that had more than doubled to 45,000 in a very rapid economic increase. And then in 2008, there was the economic crash where it went down by almost 20% in a single year to $35,000. So this rapid growth was sometimes referred to as the Celtic tiger. And the, yes?
These contemporaneous US dollars or?
They're purchasing power parity, which means it's a
US dollar in the particular year.
No, it's adjusted to, I think it might be 2013 dollars, but in purchasing power parity at the time, so adjusted for inflation as well as, but I think it's 2013 dollars. The 2008 financial crisis was a global crisis, as we know, but it affected Ireland worse than most other countries, except a few other countries in Southern Europe, as you can kind of infer from that plot. And in Ireland, perhaps more than in many other countries, it was associated with malfeasance and a certain number of banking scandals. And since then, there's been great interest in ascertaining the roots of the crisis. In Ireland, there were a number of parliamentary inquiries and also criminal proceedings, and I believe that some bankers actually went to prison, right, which did not happen in many other countries. But there's also interest not just finding out who was to blame, but also what the more structural roots of the problem were. And one factor that was hypothesized is the growth in the prevalence of interlocking directorships among companies. And that basically means you have two companies and their boards share at least one director. And so this was hypothesized to contribute to, as a factor to the crisis for various reasons. One basic idea is it may have contributed to groupthink and sort of prevented the mechanisms of capitalism, if you like, of different companies, at least some reacting and seeing what was happening, and also a lack of autonomy of individual companies. And in the business and organizations literature, interlocking directorships have been associated with quite a few things, many of them not positive: poor performance of companies, social embeddedness that limits their effectiveness, excessive remuneration of directors, conflicts of interest, and also lack of diversity, because the interlocking directorships, it's kind of associated with sort of old boys club, and tends to, has been found to effectively reduce the number of women, and more recently possibly minorities. And the positive side is it may promote sharing of knowledge between companies and sectors. So what we wanted to see basically, was there anything to this, and in particular, had there been really a growth in prevalence of interlockingness over this period, and what had happened since the crash. So the study here consisted of the top 100 companies listed on the Irish Stock Exchange over the 11-year period from 2003 to 2013, which encompassed the end of the Celtic tiger and the crash and its aftermath. And we got a list of companies and their directors from the Irish Stock Exchange. And I will say this was actually not a trivial thing at all. To get these data, they were in terrible shape when we got them. To get them into a shape that we could analyze them took about 9 months of hard work. And as a statistician, I'm used to scientists coming and kind of saying, here are our data, and can you help us analyze them? And this is one of the very few times I've actually collected data, so I emerged with a heightened respect for people who collect their own data. So we organized the data into a dynamic bipartite graph. So each year of the 11 years, edges were created between directors and the boards of which they were members. And since our main focus was on company interlocks, we removed companies that did not involve any interlocking links in any of the years. These were often kind of small, family-controlled businesses that were kind of not really in the sort of, let's say, ecosystem that we were interested in studying. And this led us to a reduced data set of 59 companies, 761 directors, and just under 4,000 edges over the 11-year period. And this is one very naive kind of exploratory analysis which tries to get at the prevalence of interlocking by looking at the proportion of directors who were interlocked in each year. And this proportion increased by 60% from 2006 to 2010. So a really dramatic increase right at the period when there was the Celtic Tiger. So that seems to provide a kind of prima facie sort of evidence, if you like, for that there is something going on here. And then it went back down in close parallel, going up with the Celtic Tiger and down with the financial crash. However, as Peter Hoff emphasized in his very nice talk yesterday, there's, this is not, if we did a binomial model or something, it'd be significant, but there's a lot of dependence in these data. There's dependence from one time point to the next, and there's dependence between directors and between companies. So a lot of dependence. So doing a kind of naive binomial model or something on these data would certainly understate dependence. So our approach is to develop a statistical model for the data, which are a dynamic bipartite network that takes account of these dependencies. And bipartite means, well, why don't I? So it means a network like this where there's two types of nodes, in this case companies and directors, and the links can go only from one kind of node to the other kind of node. So in this case, directors can be linked to the boards of which they're members. Okay, and so we model positions of companies and their directors using a latent space model, which Peter Hoff talked about yesterday in his talk. We model the positions in a d-dimensional latent Euclidean space so that a director who lies closer to a company will be more likely to sit on that company board. And so I want to briefly review the most relevant literature. The latent position model was introduced by Hoff et al. In 2002, and Peter gave a brief review of it yesterday. And this was a model for unipartite static networks. And here we're looking at dynamic bipartite graphs. And data here, Yij is 1 if there's a link between the actors I and j, 0 if not. And the model basically says if Pij is the probability that Yij equals 1, then it's modeled on a logistic scale where basically the idea is that each actor has an unobserved latent position in a d-dimensional Euclidean space, and when the latent positions are close together, the actors are more likely to be linked. Okay, and this is modeled by a logistic regression model with the parameter alpha, which is the intercept, kind of governs the overall density, and then the Euclidean distance here. And particularly in Bayesian analysis of these models, the zi's have to be inferred, and often they're given a model which could be a normal model or maybe a mixture of normals if we're interested in clustering kind of situations. And one reason this has been quite popular over the past 15 years, and I think as Peter told us, it automatically accounts for transitivity and homophily, which are some other statistical models for networks struggle to do, and which is a major feature of most social networks. And as Peter also pointed out yesterday, it's not necessarily, there are other kinds of networks where it's not necessarily a dominant feature, but almost all of social life is, transitivity is a huge feature. If I'm Peter's friend and, Peter is Pierre's friend, then I'm more likely to be Pierre's friend. And this is the way social life works. So there's been a literature moving this in the direction of dynamic bipartite graphs. The dynamic latent position model, basically here we've got data which is indexed by time t. And so the latent space evolves over time, and each latent position evolves according to a multivariate random walk here. And this was proposed actually fairly shortly after the original latent position model by Sarkar and Moore. And there's a paper in JASA last year by Sewell and Chen that basically proposed more refined ways of estimating it, a kind of Bayesian approach. The Sarkar and Moore was a kind of machine learning, sort of just a brute kind of optimization approach, but this was but dealt with the same model. So dynamic bipartite latent position model basically just refers to data, and here I'll use director and board, although it can be any bipartite situation. So Yij t is 1 if director I sits on board j in year t, 0 if not. And then the model, basically we have a latent position model where directors have positions in the latent space and boards have positions in the latent space. And you can only have distances between them. I mean, that because there are only links between them. And both director positions and board positions evolve according to random walk. And this is similar to a model proposed by Sarkar et al. In 2007. Not exactly the same. Sarkar et al. Used kind of squared the distance in that paper, and there's been subsequent literature. So, so we kind of, this looked good. We applied it to our data, and it didn't work at all. So and the problem was there was much more time dependence in the data than this model allows for. The latent space didn't capture the time dependence. And actually, after thinking about it, there's a very simple reason, which is that basically just a very simple mechanistic reason, which is if somebody's on a board 1 year, they're much more likely to be kept on it the next year. And latent space can't capture that. The latent space model has people bopping in on and off boards. So, and that's a huge part of the dependence. But scientifically, it's not terribly interesting because when you think about it, well, it's kind of obvious. People stay on boards for 2, 3, 4, 5 years. We basically proposed an extension of the model that takes account of this and has, in addition to latent space dependence, it has conditional Markov dependence. And it looks like this. So here we have this term here, which previously was just alpha, an intercept alpha. There are two terms. So there's, if between I and j at the previous time point there was a link, then the intercept is gamma t, and we refer to this as the edge persistence parameter, and it models the fact that once an edge is formed at time t, it tends to persist over time. And then here, this is if there was not a link at the previous time point, the probability or the intercept is beta t, and this we call this the non-edge persistence parameter, and this captures the fact that a non-edge at time t also typically persists over time. We found empirically the director positions changed very little over time, partly I think for an individual director position, because typically they were on very few boards, there wasn't a lot of information. But they were much more expensive to infer because there were about 15,000 of them or something. So we kept them fixed, which didn't really impact conclusions. Modeling the positions, again, the board positions follow a multivariate random walk where these epsilon innovations are multivariate normal. And so the first time a board appeared on the stock exchange, we actually started by modeling them with a kind of Ornstein-Uhlenbeck or actually AR1 model, and then sampling from the equilibrium distribution, but that didn't work very well. So we just allowed the first one. We gave it its own variance parameter here, or its own precision parameter, tau 0 w, and the director positions then were sampled from a normal distribution. And the edge persistence parameters were also allowed to follow a random walk, and again with the first one being drawn from a normal distribution, with a similar model for the non-edge persistence parameters. And the precision parameters were modeled by gamma distributions with a common shape and rate, and then there were 3 user-specified hyperparameters. Okay, so and in terms of estimation, we considered a contribution of a board to the likelihood only in those years where it was actually on the Irish Stock Exchange, in other words, where it existed from this point of view. And you could think when it didn't, it was missing data, but we actually felt it wasn't really missing data, it just was non-existent data, which is a different thing. If the company didn't exist, there was no position. And similarly, contribution of a director was considered only in the years where he or she sat on at least one board. And we used MCMC, and one well-known issue in latent position models for networks and more generally is the likelihood is invariant to rotations, reflections, and translations. So we want an inference that basically allows us to make inference about the distances which are identified, and not the positions themselves, which aren't. So we post-processed this using Procrustes matching, which is the standard approach to this, and was in Hoff et al. And has been used in most of the papers since then. Okay, so this is, if you like, this shows the evolution of the average board positions where they went over time from red to yellow. So the boards were in red to yellow, and the director positions, which were fixed, are in blue. So you can see there's some movement there, and let's try and, okay. So here we actually have, this was produced by Niall, I have to say, and it actually works, which doesn't always happen in these things. So this shows the evolution over time in a sort of dynamic. Maybe I'll slow it down a little bit. So this is starting 2003, and you can see the red. The positions of the boards are in red. The positions of the directors are in blue. And let's look at it again. And I think here you can see that over time it started off pretty spread out and becomes more compact over time. We'll just do one more sort of run of it, and I think it sort of looks like there's a compactification of the space over time. But to really assess that, we need to do statistics. So okay, see, now we have. It doesn't want to. Okay, so so one question is there really evidence both of the latent space? And one of the things when we found out we had sort of that the latent space wasn't capturing all the dependence, we then wondered, well, actually, after you take account of this tendency of directorships to continue, is there anything left? In other words, is there really a latent space? And another thing is, well, just to back up the evidence that there is a need for the Markov chain. So we compared 3 models. We compared our model with 2 simpler models. So here, model 1 is the latent space model we've just described. Model 2 will be a special case where the latent distances are all 0. So basically no latent space. And this model comparison be used to test, basically, is the latent space explaining anything? And model 3 was a special case of model 1 where the Markov chain dependence is omitted, and we just have the latent space. And so we used DIC, although we'll see the differences are so big that it sort of doesn't matter probably what criterion you use. So the smaller DICs are better. And the proposed model had a DIC of just over 7,500, and you can see here the 2,300 actual parameters, but little under 800 effective parameters according to the DIC count. If you have no latent space, the DIC is up above 10,000. So there's a huge difference, and the latent space is actually explaining a lot of what's going on. And then, of course, the number of parameters is a lot lower. And if we have no Markov chain, things are even worse. And this is a latent space, but no Markov chain. So actually, the Markov chain is probably explaining more of the dependence than the latent space. But you need both. Okay, so the goal of all this is yeah. Am I? Can I have an extra minute to deal? Or why don't you? Because Peter's a hard taskmaster here, as I know from long experience. So the posterior distribution so basically the goal of this is to quantify and track the evolution of interlockingness. The posterior distribution of latent positions can be used to derive a metric of interlockingness in each year. And we actually just use we assess the variation of interlocking through the empirical variance of the boards, which is just given by this. So how much what's the overall variance of the boards? And that is a posterior distribution. And here we see, so this is the result in this plot, in a sense, is kind of the punchline. We see this is the variance, empirical variance of active boards. So basically, our contention is the more interlocking, the less variance, right? Because the closer the board positions are. And we see it started off up here, and then over the period from 2005 to 2009, which is the kind of white-hot end of the Celtic Tiger when things were really crazy in Ireland, there was a rapid decline in the variance, and so an increase in interlockingness. Interesting thing here is that from the crash onwards, it doesn't seem, we saw when we did the naive analysis that it looked like interlockingness was going down, so this confirms that interlockingness went up during the Celtic Tiger, but it suggests that after the crash, there isn't much evidence of a change. So it suggests that actually that that kind of decline that we saw could be due to it could be an artifact that due to dependence. So the interlockingness increased during the end of the Celtic Tiger up to the crash, and since then there's not much evidence of systematic change. And this inference accounts for temporal between company and between director dependence. So one question we can ask is, what form did this take? And the obvious one we'd think of is, was it due to established companies appointing common directors? So that's one would think that would be increasing. And that's the first explanation that springs to mind, right? More common directors. But actually, it's not the only possible, let's say, description. It could be that new companies that were established during the end of the Celtic Tiger were actually more interlocked. So they were, if hypothetically you had new companies who were maybe trading more on links to existing companies, or to less interlocked companies leaving the Irish Stock Exchange. So maybe isolated companies were, going out of business at a faster rate during that period. Here we have, this is the plot I showed you before, and one way to kind of get a handle on this would be to just look at companies that were present, established companies that were present for all 11 years. And that was a bit less than half of all companies. And we actually see, this is what we see here. So if we just look at companies that were active in every single year, there's actually no evidence of change at all. So this means that this change is really due to companies that were either joining the stock exchange or leaving. That means really coming into existence as public companies or going out of existence for one reason or another. And I looked at this a little bit. The average distance from the center was around 6, and in the plot, And so we saw 6 companies far from the center left the stock exchange over that period, and 7 joined. So the inference is, and this is an example here, this is one that was present, was very far from the center, so distance 12, and it went out of business 2007. And here we have another one that was close to the center with a distance of 3, and it also had a pretty constant, it came into existence in 2007. So you had sort of isolated companies being replaced by interlocked companies is kind of the story. So to summarize, we've proposed a new latent space model for dynamic bipartite networks that can capture edge persistence beyond the latent space, and it goes beyond the literature on this, which seems to have missed this often important fact, as indeed we did. We found the interlockingness of company boards in Ireland increased during the end of the Celtic Tiger, closely paralleling the rapid economic growth. And actually, this seems to reflect non-interlocked companies leaving the stock exchange and interlocked companies joining it, and not what you might first think, which is established companies getting more interlocked. And these results are at least compatible with the view in the, let's say, business literature that there are disadvantages to interlocking. And it is possible, although we certainly haven't proved it, that an increase in the amount of interlocking may be a warning sign of and possible contributing factor to future financial instability. So it could be maybe used to monitor economies for signs of overheating. So the paper this was based on was published in PNAS, just 2 months ago, was it? No, I think. And there's some other papers on kind of latent space position models, which are references at this website. So thank you.
Questions? Just a quick question on presentation. Can you go back 3 slides?
Oh, let me
get to your
yeah,
variance of the W's, the interlocking this measure.
I'm going
just what does the scale mean?
So the scale, let's see, the scale doesn't mean anything.
but the W's are on the scale of the logit probabilities. So presumably there's a way to link them back to the probability scale so we can actually get a feeling for what they mean.
There would be, yes, and I didn't actually do that, so that's a really good question, and it's one of the things one shouldn't do in public is try and do that kind of calculation, but that's a really good point actually. Yeah.
So just described what I think is a very typical modeling process. You look at the data, you try something, then it doesn't work, you try something else. And of course the problem is by the time we actually apply a model to the data and predict something, we're brutally confounded. Right? because we've looked at the data like 50 times. And of course, that problem arises everywhere, but I feel that it's maybe particularly problematic in network analysis because we neither have off-the-shelf models, nor can we do proper data splitting. So, can you comment on that as somebody with a lot of applied experience?
Yeah, I mean, I think you've just described the way science actually works. So it doesn't bother me. I think it's the way things work, and I think we did in this process, through looking at the data, the subject matter literature, talking to people, and so on, and also seeing what happened in the data. We did discover some new things and a model that accounted for them. So I'm not that doesn't bother me at all. I mean, some economists used to be dismissive of what they call data mining, but I think there's been a general acknowledgement that that's the way science actually works. Oh, okay. Well, Peter, Peter Bickle. Yeah.
I have just a question. Did you look at the pool of directors that was available during this period? Because it could be right that there's just a small group of people who are viewed as having enough experience for the companies that.
Yep. So there were just about 1,000 people were directors during that over the period, and 761 of these were directors of companies that had some degree of interlocking. The number of directors who were actually involved in interlocking was a lot smaller than that. It was only about 10%. So you were looking at, and we did look. Yeah, we looked. I mean, we looked actually at who these people were, and we looked at their CVs and they were. There was maybe 70 people who were involved in these interlocks and who were clearly very central in the economy and so on. So I think that, but I don't know what we can. I mean, draw from that.
What about second order interlocking? It goes on all the time.
Yeah, you mean second order?
That would be lagged effects across directors.
Yeah, and we just looked at simultaneous ones, but there could be lagged effects, which we didn't look at. But again, that could be interesting.
Maybe one more question while Pierre sets up.
Okay, well, Sonia tried to get her.
So when you show the plot of your question or not? I can.
Yeah, no, go ahead.
No, I mean, I'm a bit concerned. What is the model bringing that was not obvious in the data?
Okay, well.
And also somehow my question is related to the last thing. So what would we really? So I think it's a great value that you collected the data, and that's as you said. Then I'm not sure that the model is discovering things that were not so obvious. And then maybe your last question was the most interesting. Can we anticipate anything?
So yeah, what's the model bringing? So basically, if you do naive kind of just proportion, you see the proportion went up and went down. But the question is that there's a lot of dependence that naive thing doesn't take account of, and there's a huge amount which Peter said. So basically, it could be it goes up. A naive thing that doesn't take account of dependence says is significant, but actually perhaps it's not significant. So taking account of the dependence is something, basically to make the inference firm, you need to take account of the dependence, and this is an effort to do that. Second thing is, you do the naive thing, it said interlockingness went up and then went down. When we took account of dependence, we found, significantly it went up, but there's no evidence it went down. So the going up was not an artifact of dependence, but the going down may have been an artifact of dependence. So basically doing the modeling, I think it actually did discover a lot of things, and that's it's the value of doing statistical modeling as distinct from just computing proportions. So I think doing the modeling did contribute something in this case, and it's something So.
All right. Well, I'm told I'm a taskmaster, so I have to